So thank you very much for the introduction. Good morning, everyone. And I'd like to thank the Technical Program Committee for inviting me and giving me the opportunity to present our work on infrared detectors based on Plasmonic Piezoelectric NEMS Resonant devices. And let me start with a little bit of introduction in general on infrared sensing technologies. So infrared sensors were originally developed to fulfill some of the most important military needs, such as night vision, missile tracking, target recognition. But the recent advancements in terms of sensor miniaturization, power efficiency, and low cost, they really enable the use of infrared sensor technologies in a large variety of consumer products. And in fact, night vision cameras, for example, are nowadays used in cars and are used to detect pedestrians that are 4 times farther than the usual headlight range, substantially. But also, relatively compact and low-power IR cameras can be attached to smart mobile devices to add interesting imaging functionalities. So infrared detectors are typically divided in 2 main categories. We have photon detectors and thermal detectors. Photon detectors rely on the interaction between electrons and photons in a semiconductor material. So these basically produce an electrical signal upon exposure to infrared radiation. So these devices are characterized by excellent resolution and fast response time, but they do require cooling in order to prevent thermally generated carriers. So they are typically bulky, expensive, and not very power efficient, and therefore not very suitable for some of the applications that I showed you earlier. On the other side, thermal detectors instead rely on a temperature-induced change in a material physical properties upon exposure to infrared radiation, and they do not require cooling. So typically, they are smaller, cheaper, and more power efficient compared to photon detectors. The performance level is not as good as photon detectors, but still good enough to fulfill the needs of several military and civilian applications. So in this talk, I will discuss a little bit about a relatively new kind of thermal detector, which basically relies on the temperature-induced shift in the mechanical resonance frequency of a nanomechanical resonator. So this kind of device basically has the same advantages of other thermal detectors in terms of power efficiency, size, and cost, but could potentially outperform other thermal detector technologies since it's substantially based on a resonant sensing mechanism. And in fact, resonant sensors in general really yield high sensitivity and low noise performance. And that is, of course, is an extremely important feature for many kinds of sensors. And in fact, this kind of nanomechanical resonant device have a mechanical resonant frequency that can be made highly sensitive to an external perturbation given the extremely small dimension of this nanomechanical element. But at the same time, these devices are also characterized by intrinsically very low noise performance due to the fact that they exploit a high quality factor mechanical resonance that substantially boosts the signal-to-noise ratio of the sensor. And in addition to that, frequency, which is the output quantity of a resonance sensor, is a quantity that can be read out with a very high accuracy. So even beyond these advantages in terms of detection capabilities, MEMS-NEMS technologies are quite unique since they can provide multiple sensing and wireless functionalities in a small footprint. And that's a really quite unique thing of MEMS technologies that really enable new devices with enhanced functionalities. And in fact, MEMS technologies have already played an important role in the development of modern smartphones and tablets. So here you see a list of MEMS-based devices that are already integrated in modern smartphones and tablets. For example, there are several RF devices, bulk acoustic wave filters and duplexes, but also different kinds of sensors, inertial unit, magnetometers, microphone pressure sensors. And there is a clear market opportunity for MEMS technologies to further expand basically the functionalities of these smartphones. And in fact, the market for MEMS in smartphones is expected to grow to about 6.4 billion in the next couple of years. And here you see just a subset of the new functionalities that are expected to be integrated in smartphones. And among those, you can see there are also infrared sensors. So another great opportunity for MEMS technology is the Internet of Things, in which basically physical and virtual objects are linked to the exploitation of sensing and wireless communication functionalities. And in order to implement such highly distributed sensing networks, we really needed wireless sensing nodes that are miniaturized, low power, multifunctional, reconfigurable. Therefore, in this area, also MEMS technology can play an important role. This is pretty much the vision that has driven the research in my group, and in particular, we have been working at the development of a core technology platform that can deliver multiple wireless and sensing functionalities in a small footprint. In particular, we have been working on an aluminum nitride piezoelectric nanoplate resonator. Basically exploits the unique and excellent piezoelectric transduction properties of ultra-thin aluminum nitride film, combined with the other interesting advanced materials such as phase change materials, graphene, 2D materials, plasmonic, metamaterials, and magnetic materials. And we use this combination to implement different kind of functionalities, going from reconfigurable RF filters to gravimetric sensors, infrared detectors, and magnetometers. And in this talk, I will focus on our effort on infrared, spectrally selective infrared detectors. Let me start telling you a little bit about the core technology that we use. So these are nanomechanical resonators. It's composed by an aluminum nitride thin film sandwiched between two metal electrodes. When an electric field is applied across the thickness of the piezoelectric layer, a contour extension of mechanical mode of vibration is excited through the D31 equivalent piezoelectric coefficient of this aluminum nitride. So the operating frequency of this laterally vibrating structure is set by the width of the plate, while the two other geometrical dimensions are substantially used to set the equivalent electrical impedance of the device. So now, by properly patterning the electrodes of the device using this interdigital configuration, it's possible to excite a higher mode of vibration in the mechanical structure. And in this case, the operating frequency of the resonator for a given material stack is set by the pitch of the interdigital electrode. So now the working principle of an infrared detector based on a piezoelectric resonator like the one that I showed you before really relies on the fact that the resonant frequency of these piezoelectric electromechanical resonators is really highly sensitive to temperature. So these devices are characterized by a temperature coefficient of frequency in the order of -30 to -100 ppm per Kelvin. So very high temperature sensitivity. So even if a small amount of infrared power is absorbed in the resonant body of the device, basically this infrared power will generate a temperature change that is quite large, given the fact that this plate is basically released from the silicon substrate, it's suspended, it's free to move, and therefore is very well isolated from the heat sink. But also this temperature variation has a relatively short time constant due to the fact that the thermal mass of this nanomechanical structure is quite small. So now this temperature variation would generate a shift in the mechanical resonant frequency of the structure, and therefore by connecting the device in the feedback loop of a sustaining amplifier, it's possible to build a frequency source that is highly sensitive to incoming infrared radiation. So basically we can monitor the variation in the output frequency of the signal that we have here at the output of this oscillator and get information about the infrared radiation that is absorbed. So now if we look at the most important metrics for thermal detectors, which are sensitivity, time constant, and noise performance, we see that these kind of piezoelectric resonant thermal detectors, they really have some quite unique enabling features. In fact, it's possible to achieve high sensitivity thanks to the intrinsically high temperature sensitivity of the device, but also thanks to the fact they can be made very well isolated from the heat sink, so at very low thermal conductance, which means high thermal sensitivity. The time constant is very low, given the very low heat capacity of the structure. So we are talking about micro nanomechanical device, so very small thermal mass, which means time constant in the order of microseconds to milliseconds. But also very important is the noise performance of the device. So these devices are based on IQ mechanical resonance. And in fact, using this kind of devices, it's possible to implement frequency sources that are characterized by a very low phase noise. So you see typically the noise-induced frequency fluctuations of this kind of devices in the order of part per billion range. So really, by combining these noise performance with the very high sensitivity of the device, it's possible potentially to achieve a figure of merit for infrared sensors that are quite promising, quite interesting. For example, noise equivalent power in the order of picowatts per square root of Earth, or a noise equivalent temperature difference in the order of a millikelvin. So, but now, in order to achieve this performance level, it's really important to follow specific design strategies for these micromechanical, nanomechanical resonators. So of course, it's really important to maximize the thermal resistance of the device and the absorption capability of the nanomechanical resonators. So the infrared radiation has to be efficiently absorbed in this resonance structure. But of course, it's also important to minimize the thermal capacitance, which substantially means scaling the volume of the device. And we need to do this thing while maintaining high quality factor, because we want to maintain the noise performance of the device, and also without sacrificing transduction efficiency, because we want to be able to connect these resonant devices to compact and low power electronics. So in other words, what is really crucial for the development of this piezoelectric resonant thermal detector is the scaling of these micromechanical elements, which really enables the capability to achieve high thermal isolation and low thermal mass. So, and this idea was proposed about 20 years ago by John Bigg, which actually demonstrated theoretically that by micromachining of quartz, it would be possible to build microresonators operating in the 200 megahertz to 1 gigahertz range that can be made very highly isolated from the heat sink, and therefore could be used as very good thermal detectors. And in fact, he demonstrated that using this approach, maintaining the high quality factor of quartz resonators, it would be possible to achieve a noise equivalent temperature difference in the order of 10 millikelvin, which is of course quite good for infrared sensors. And this idea was experimentally demonstrated a few years ago by Srinivas Tadigadapa group at Penn State. They actually showed that by basically micromachining a quartz substrate, it's possible to build resonators with a device thickness in the order of few microns that actually have very large temperature sensitivity. They are very well isolated from the heat sink. You see 4.6 10 to the 3 Kelvin per watt, so they're very well isolated. Small thermal capacitance, and of course, they still have excellent noise performance due to the very good quality factor of quartz resonators. And in fact, they demonstrated the capability of achieving noise equivalent power in the order of 3.9 nanowatts per square root of Earth. More recently, some excellent work has been done also by Mina Raiz-Zadeh group at the University of Michigan. They actually demonstrated that further miniaturization and dense integration of resonant thermal detectors, it's possible by using thin film piezoelectric materials rather than a bulk substrate like quartz. And in fact, they demonstrated resonant thermal detector using thin film gallium nitride with a device thickness in the order of a micron. And as you can see here, by scaling the dimension of the device, they were able to achieve thermal capacity in the order of under 35 nanojoule per Kelvin, so much, 1 order of magnitude improvement in thermal capacity. This is a smaller device. But despite this scaling, they were still able to maintain good noise performance and demonstrated noise equivalent power in the order of hundreds of nanowatts per square root of Hertz. And I think in some more recent work, probably they were able to push this down further. So in our group, instead, we have been focusing on thin film aluminum nitride-based piezoelectric resonators. And we did that because we believe aluminum nitride thin film resonators have some unique advantages compared to other piezoelectric materials. So one key thing here is that ultra-thin aluminum nitride film, as thin as 50 nanometers, can be deposited by a low temperature sputtering process on any substrate. And in fact, we actually demonstrated resonators that are as thin as 50 nanometers. So that's quite promising and important for this kind of thermal detectors. But in general, for resonant sensors, scaling of the resonant device is a key element. And we can do that with aluminum nitride thin film, maintaining at the same time very good transduction capability. So the piezoelectric properties of such thin film aluminum nitride is still maintained even in this reduced dimension. And thanks to high quality factor, large electromechanical coupling coefficient, the equivalent electrical impedance of this kind of device is quite low, and therefore this device can be directly connected in the feedback loop of a simple and low power sustaining amplifier. So here you see an example I'll show you later of a very simple amplifier based on a 0.5 micron CMOS technology. So this really enabled the implementation of resonant sensors that have high performance, but also with a low power electronic readout. And here this is just a quick summary of the things that we demonstrated, more or less. The temperature coefficient of frequency in the order between -28 and -57 ppm per Kelvin. given the small dimension of this device and some other tricks that I'll describe later, we can achieve very high thermal isolation, so 2 order of magnitude improvement in thermal isolation compared to other demonstrations. These devices are characterized by a very small thermal capacitance since they are very tiny, and still they have very good noise performance because, as I will show you later, despite this scaling, we can still maintain good high quality factors. So we demonstrated noise equivalent power as low as a few hundreds of picowatts per square root of Earth, with a thermal time constant ranging between 11 microseconds and 20 milliseconds, depending on the particular design. So, but let me tell you a little bit more about the specific design of the resonator in order to implement a good thermal detector. So, as I mentioned, a key thing for this kind of resonant thermal detector is the isolation from the heat sink. And that is really determined by the thermal resistance of these anchors that substantially anchor the resonant plate of the device to the substrate. So in general, in order to maximize the thermal isolation, it would be needed to basically minimize the cross-section of these anchors. But now the cross-section of this anchor is really limited by the need of a thin metal layer for electrical routing. So we need to provide an electrical routing from the device terminal to these electrodes that are patterned on the resonant body of the device. So the design solution that we propose basically involves removing the piezoelectric layer from the anchors and basically use very thin nanoscale anchors with a minimum cross-section to anchor the device to the substrate and simultaneously provide the electrical routing needed for the signal. So this really minimizes the size of the anchor and maximizes the thermal resistance. So, but now, given this large thermal resistance, if you want to maintain a relatively low time constant, what is really crucial is to scale the volume of the device. Right? We need to reduce the thermal capacitance of the resonator. And in principle, lateral scaling of the device would be sufficient in order to reduce the volume and therefore reduce the thermal capacitance. But the problem is that simple lateral scaling would drastically reduce the electrical capacitance of these piezoelectric transducers substantially, and that would become substantially comparable to parasitics that are on the substrate, and that would drastically reduce the transduction efficiency of the device. So basically, we would couple a lot of energy to parasitics rather than the piezoelectric resonator itself. So in order to scale the volume of the device while maintaining a pretty much constant value of electrical capacitance, which sets the impedance of the device, what is really key is to scale the thickness of the piezoelectric layer. So basically, that's why we like to call this device a nanoplate resonator, because that's really a key feature that enables a lot of sensing capabilities. And in fact, to build high-performance resonant thermal sensors, we need can be really implemented using a high-Q nanoplate, which is basically anchored to the substrate using these tiny metal anchors. So based on these simple ideas, we developed a fabrication process that basically can selectively remove the piezoelectric material from the anchors, as you can see here. So the device is composed by thin film aluminum nitride plates, so typically that was between 500 nanometers and 50 nanometers, platinum electrode on the bottom, and another metal electrode on top, and I will talk a little bit more later about how we can get absorption, infrared absorption in this kind of devices. But you see the device is anchored to the substrate only using these platinum metal anchors. And here you see one of the prototypes that we demonstrated. So these are 500 nanometer thick aluminum nitride plate, which is anchored to the substrate using these very tiny metal anchors. So you see the anchor is only 100 nanometer platinum thick, and the width is about 3 microns. So what is very interesting, first of all, it's the electromechanical performance of these devices, right? So we measured the electromechanical performance of the device. So here you see the admittance curve of these prototypes. And you see the quality factor is quite high, the order of 3,000. And what is even more interesting is that we built about 17 devices, and we looked at the quality factor of devices with metal anchors or with more conventional piezoelectric anchors, like thicker anchors. And what we noticed is that there is an average Q improvement of about 28%. Of course, this is not large enough statistical data to be conclusive, but definitely looks like that by using these very tiny anchors, basically having these large acoustic mismatch between the piezoelectric resonant plate and the anchor itself helps in confining the acoustic energy in the resonant body of the device. So we can basically achieve very large thermal resistance, but at the same time, high quality factor and good electromechanical performance in general. So we characterize, of course, we connected this device to a low power CMOS oscillator. So this was built in the 0.5 micron CMOS process. So in this particular case, the power consumption was in the order of a milliwatt. And we characterized the thermal sensitivity and the noise performance of this oscillator, and we were able to extract a noise equivalent power in the order of 300 picowatts per square root of Hertz. So then now, if you compare all these, basically performance of the device with the more conventional kind of thermal detectors, we see that these are already comparable to the state-of-the-art uncooled infrared detectors. So it's very, very promising and very interesting for this technology. But now, one very important challenge that we have with these piezoelectric resonant thermal detectors in general is that the infrared absorption in such ultra-thin aluminum nitride piezoelectric plate is quite weak. So here you see the infrared absorption spectrum of a 500 nanometer thick aluminum nitride film measured in the 2 to 16 micron range. And you can see beyond these two basically vibrational rotational peaks of the aluminum nitride, the infrared absorption is quite low. So the conventional approach to solve this issue involves integrating an absorbing material or a material stack. So actually, for example, lossy dielectrics like silicon nitride or a metal insulator metal sort of grating on top of the resonant device. So that approach, of course, improves the infrared absorption of the device, but also typically degrades the electromechanical performance and the thermal sensitivity of the device. Right? As I showed you before, there is what we really want to do is scale the dimensions, make the device as small as possible, maintaining the high quality factor and transduction efficiency. And so this approach goes a little bit against that trend, right? So the way we are trying to solve this fundamental issue is to instead use a piezoelectric plasmonic metasurface to form the resonant body of a nanomechanical resonator with simultaneously tailored optical and electromechanical properties. So basically, the idea here is to pattern the electrodes of the device such a way to simultaneously excite a mechanical and electromechanical resonance in the same ultra-thin piezoelectric material. And in fact, and then basically by exploiting the intrinsically high thermomechanical coupling between these two resonances, we can achieve high sensitivity to infrared radiation. So and this, in fact, can be done by basically patterning sort of plasmonic nanostructures. So in this example is just an array of small patches, substantially. And these are basically act to tailor the surface reactance of the structure to be largely capacitive, and therefore it can induce a Fabry-Perot-like resonance, but in a deeply sub-wavelength aluminum nitride plate. So even though this thickness is only 500 nanometer, we can absorb radiation in the order of, as I will show you later, for example, about 8 micron. And what is very interesting here is that now the frequency of this electromagnetic resonance, right, this absorption frequency, really depends on the lateral dimensions of these patches that you can see in this expression here. So basically, it's possible to lithographically tune the absorption band of these devices by changing the dimensions of these plasmonic nanostructures. So, and in fact, here, you see some of the plasmonic piezoelectric metasurface that we built. So we demonstrated that it's possible to achieve in a 500 nanometer thick aluminum nitride film. It's possible to achieve absorption peaks in the order of about 80%. And indeed, it's possible to lithographically tune the absorption frequency of the structure. So based on these ideas, we built the first prototype of a plasmonic piezoelectric nanomechanical resonator. So you see the device right here. Here is a cross-section of the device. The interdigital electrode is patterned on the bottom of the device, and that is used to basically excite a higher, in this case, a third-order counter-extensional mode of vibration, mechanical vibration in the plate, while the top electrode, or the top metal layer, is substantially two functional areas. One with these nanoplasmonic structures that we use to basically confine the electromagnetic radiation in the body of this piezoelectric structure, and also a continuous metal plate, and instead it's used to improve the confinement of the excitation electric field provided by the bottom electrode. So as you can see, the device here is quite thin, and it's, again, connected to the substrate using those tiny metal anchors that I described before. Given this particular design, we measured, again, a relatively high purity factor, and there was above 1,000 for this prototype. But what is very interesting here is that now if we measure the absorption spectrum of these nanomechanical resonator, well, now we have a very nice absorption band here, which is about 80% absorption at the peak point, centered around 8.8 microns for this particular example. So now we tested this prototype. We exposed it to a 1500 Kelvin glow bar with an emission band between 2 and 16 micron. So despite this broad emission of the source compared to the very relatively narrow absorption band of the device, still we were able to measure an improvement in responsivity for the device compared to a conventional nanomechanical piezoelectric resonator, thanks to the improvement associated with these nano-plasmonic structures that we put there. And we measured, of course, the noise performance, the thermal sensitivities, and for this prototype of spectrally selective IR detector, we measured the noise equivalent power about 2.1 nanowatts per square root of Earth, which is really among the best that, to our knowledge at least, compared to other spectrally selective thermal detectors. What I'm showing you in this plot is that still, although we are quite happy with this performance, there is still a relatively large gap between the measured noise, the resolution of the device, and the theoretical limit that is set by thermomechanical noise and thermal fluctuation noise. So definitely there is still margin to improve the performance of this device, and that involves really understanding what are the main noise sources that are adding basically noise to the system in addition to the fundamental thermomechanical noise. So what also very interesting about this is that now by changing the pattern of these plasmonic structures, so for example, here you see a slightly different example, and we have a sort of a complementary structure, so we call it a fishnet metasurface. It's possible to completely change the absorption properties of this device. So in this case, we have a broader absorption centered around 4 microns, for example. And again, still, the performance, electromechanical performance of the device, they're not really affected by that. And these concepts can be potentially extended also longer wavelengths. So for example, using concepts that have been very well developed in the photonic metamaterial community, for example, using electric ring resonators and things like that. And that, of course, is a really high potential in the terahertz, in the 1 to 30 terahertz range, where there is a large need of basically uncooled thermal detectors that are miniaturized and low power and so forth. And also spectrally selective, so opening interesting opportunities for multispectral imaging and spectroscopy applications. So in conclusion, what we demonstrated is that in fact it's possible to combine electromechanical and electromagnetic resonance in a single ultra-thin piezoelectric film and use that idea to build basically plasmonic resonators that are quite interesting and unique sensing, infrared sensing performance. And just one quick thing before I finish this. We have an open position in my group now for a postdoc. This is a very interesting new DARPA-funded program. It's a near zero power program from DARPA in which we are going to extend some of the concept that we developed for this infrared detector technology to build a different kind of, basically extremely low power, actually zero power sensor. So if anyone is interested, please contact me. And just let me acknowledge the group members, collaborators, and of course the funding agencies. Thank you very much for your attention.